So I wanted to start by introducing my co-authors. Sorry for...
Can you speak up?
Sorry. So I want to introduce my co-authors, these three guys. Sorry for the low quality pictures. There's Adam, he's at MIT, he's a student. Robin's at Microsoft, and Avishay's a postdoc at Stanford. And I think he even has a talk tomorrow, so go to that. And this is what they all look like, so you can ask them about the paper. All right, so broadly speaking, the paper is on a quantum advantage. So we want to find something that quantum computers can do that classical computers can't. And obviously there's a ton of work on that, so we want to focus on something that we can prove unconditionally. And this breaks a lot of things that you might have previously thought of as quantum advantage. So Shor's algorithm, for instance, shows that factoring is easy, and we think maybe factoring is hard classically, but we don't know for sure. This is not an assumption, so this is not what we're looking for. Boson sampling is also one of these problems that has hardness assumptions. In fact, most of the sampling hardness stuff assumes, say, that the polynomial hierarchy does not collapse. And Grover's algorithm, this is at least unconditional, but it's an oracle model of computation that we won't want to use for this talk. If you have to actually implement the oracle, you run into some problems. We can no longer show the quantum advantage. But fortunately, there was this breakthrough result at last QIP, the Bravi-Gossett-Koenig result, so the same one the last talk was based on, that says that there's a problem that could be solved by constant depth quantum circuits, but not by constant depth classical circuits. And this is perfect, right? This is a fair comparison between quantum and classical models. There's no conditions whatsoever on the proof. And the quantum circuit is even simple. They have a version of it that uses only local gates on a two-dimensional grid. So it's maybe even practical to implement soon. The problem with all of it is that it doesn't use any circuit complexity theory, right? Some of you may see that as an advantage, but it's not. It's an opportunity to use some of this stuff that's been developed over, I don't know, the last 40 or 50 years at least, to improve this result and get something a little better. And so that's what we try to do in this talk. So let me just take a moment and introduce all the complexity classes that we need, and there's only 3 of them. And they're all of the form, the class of problems that are solved by some constant depth circuit, either constant or classical or quantum, and using either constant or unbounded fan-in gates. So classically we have NC0 and AC0. The first one you only get constant fan-in gates, so 2 input ANDs and ORs and NOT gates. And then AC0 has unbounded fan-in gates, so AND gates that can have any number of inputs that you like. And then classically, or quantumly, we only care about constant fan-in gates, QNC0. We'll ignore this other class, but you can define something in that corner if you like. Okay, good. So, whoops. Technically, the classes I've described here should be for decision problems, right? Problems where you output just one bit that's yes or no. And we need to use them for relation problems, where you output many bits and there might even be more than one acceptable answer. And we sort of have to do this. If you just consider decision problems, then constant depth classical circuits and quantum circuits have the same power. They solve exactly the same problems. So we're just going to use these names for relation problems. So with that said, the Bravi-Gossett-Koenig result says that there's a problem in QNC0 that's not in NC0, right? So constant depth quantum, but not constant depth classical. And our result is a slight improvement where we replace the classical hardness with AC0. So it can now use unbounded gates, and even still it can't do what the quantum circuit did. And we use a slightly different problem. Okay? So this is what we're going for. Let me stop and outline the rest of the talk. So there are two parts. There will be a main results section where I try to get through as much of the proof as possible, and then sort of extras at the end where I make wild claims about other things that we can prove. And the main result, I have to break that into two parts as well. So first we start with a weaker problem that isn't quite in NC0. It's in what's called QNC0/QPoly, meaning that we need to feed it a special quantum state in order for it to do the computation. But it's still AC0 hard. And we have to show that it has this quantum circuit with advice, and then we have to prove that it's classically hard. And we'll do the proof for the classical hardness in 3 steps. First, we'll prove that it's hard as a game, then that it's hard against NC0 circuits, and then that it's hard against AC0 circuits. Okay, sort of a progression. And then once we understand this problem, we'll tweak it just a little bit, relax the problem so that it can actually be computed in QNC0. We'll sort of construct it in a way that there is a QNC0 circuit. No extra state is needed. And well, then we'll have to verify that the algorithm works and the classical hardness hasn't been damaged, but that'll be fine. And then we'll talk about other claims, better parameters, geometric locality, relating it back to the Browey-Gossett-Koenig function, and so forth. Okay, so the first step is the parity halving problem. So let me introduce that. So just a little bit of notation. The Hamming weight of a bit string is just the sum of the bits, and we'll denote it with bars around the bit string. And then the problem, the parity halving problem, is just you're given a bit string that has even parity, even Hamming weight, and you want to output another bit string y that has the same length such that this condition here holds. So the Hamming weight of y is half the Hamming weight of x modulo 2. Okay, it's sort of having the Hamming weight, but we only care modulo 2. So an example, if you have n equals 3, right, there's only 4 bit strings with even parity. They're on the left here. And okay, so the first one, 0, 0, 0, that has Hamming weight 0. And so you divide that by 2, you get 0, and you're supposed to output, therefore, a string with Hamming weight 0 mod 2. The other 3 all have Hamming weight 2, right? So you divide that by 2, you get 1. You want to output something that has Hamming weight 1 mod 2. So that'd be any of these odd parity things. Okay, so that's the n equals 3 case. Obviously, it generalizes to larger n. And I think it's quite natural to think of it as a game, right? You have n inputs, n and n outputs. Why not have n players? So we define an n-local or non-local n-player game where each player gets one of the inputs and they're responsible for one of the outputs, and they win if exactly the same condition is specified. Now, this is not a new game. It's been considered before. So the n equals 3 case is the GHZ game, which you've heard about from Matt. It's a key part of the Browey-Gossett-Koenig result. And the general case has also been studied before, first by Merman and then by Broussard, Broadbent, and Tapp much later. I think these were completely independent, but I'm not sure. Anyway, it's not a new game. In fact, some people may know this as Merman's game, although there's apparently another game that's also Merman's game. Anyway, so both of these papers prove the sort of basic results about the game that we're going to need. That there's a quantum strategy when you have an entangled state, and that it's classically hard. So let's go quickly through those. So the special state we're going to need is the cat state. right? The superposition of zeros and ones. And if you have the state, then the quantum players can always win the game. And the proof is pretty straightforward, or the strategy is straightforward. So what the players do is everyone applies a phase gate to their share of the cat state, if and only if their qubit is 1, their input qubit. And so what this phase gate does is it puts an I phase on the one branch of the cat state, but not the other. And since they're applying it when their bit is 1, you get a total phase of I to the Hamming weight of x on the one branch. Okay? Now, the problem is defined so that the Hamming weight of x is even. So we end up with one of these two states, either zeros plus ones or zeros minus ones. And you can check that if you happen to apply Hadamard's to all the bits, you'll get either a superposition of all even parity strings or a superposition of all odd parity strings. And by a strange coincidence, we want to output an even parity string in this case and an odd parity string in this case. So what the players do after they've applied their phase gates is apply Hadamard's, measure, and output their qubits. Right? So pretty straightforward strategy. This is what it looks like as a quantum circuit. So here's the cat state coming in and the inputs. They apply their phase gates, the Hadamard's, measure, and then that's your output. Okay? So that's the entire quantum strategy. This state is unfortunately necessary because you can't construct it in QNC0. We'll fix that later. The other half is the deterministic hardness, the fact that there's no deterministic strategy. And for this, I'm mostly going to refer you to this paper. But the statement you get is that any deterministic strategy, if you feed it just a random input, uniformly random over n-bit strings, then the probability the algorithm succeeds is at most a half plus exponentially small. And you can actually get very specific about how exponentially small. This is exactly tight. In fact, exercise, find the strategy that achieves this. Okay, so I guess the vague intuition is something like the parity of y that you get when the players play. No matter what they do, it'll be a linear function of the inputs, and then you can do a calculation to show that the correlation between a linear function and what you actually want is small, and so this probability has to be close to a half. All right, so that's the game part of this. We've shown the strategy, and we've shown that it's hard as a game. The next step is to prove hardness against NC0. Okay, any questions? All right, we'll move on. So the way I want to prove hardness against NC0 is by talking about locality. So a circuit is L local if each output bit depends on L input bits, at most L input bits. And so, for instance, if you had a strategy for the game, it immediately gives you a one local circuit because each person only looks at one input bit before deciding their output. And it doesn't take much work to improve the hardness result for the game to a hardness result for one local circuits. It's basically the same proof. I won't show it to you. But you get exactly the same sort of result, that on a random input, you succeed with half plus exponentially small. All right, so the big question is, what do you do when the locality is larger? And sort of the only idea that works is to reduce back down to the one local case and use the hardness there. So say fill in values for some of the inputs in a way that reduces the locality of the circuit, and then it's one local and solving a problem that you understand, so you get the hardness that you had before. So let's talk more precisely about how we do this. And the first step is this technical lemma, that if you have a circuit with some number of inputs and some number of outputs and locality L, then you can find a sort of a large subset of the inputs, n over L squared, such that if you restrict everything else, you set it to 0 or 1, it doesn't really matter, then the circuit you get at the end is one local. Okay? And this is easy enough. I can do it on one slide. You construct this graph on all the input bits. Okay? And you construct an edge between two inputs if they affect the same output, right? Because if two inputs affect the same output, you don't want to ever keep both of them, because then your circuit won't be one local. So in some sense, what you're trying to find in this graph is an independent set, a collection of inputs where none of their light cones overlap with each other pairwise. Okay? But there's a graph theory theorem, Turan's theorem, that says that the largest independent set has the size at least n squared over the number of edges, more or less. And we can show that the number of edges is at most this, and you put the two together, you get this bound at the top. Okay? So we can find this large set of inputs such that if you restrict everything else, you get a one local circuit. But what happens when we restrict a circuit for the parity halving problem? Oh, sorry, unrelated. Well, this is about light cones overlapping, sorry. Okay, so what happens if you have a circuit for the parity halving problem and you fix some of the input bits? Well, for example, if you fix one of them to 1, then the parity of your input is supposed to be even. So on the remaining bits, the parity has to be odd. So whatever problem it's solving is different from the problem we started with. But I claim that it's one of 4 very closely related variants of our original problem. Basically because to satisfy this condition, you only need to know the Hamming weight of the input mod 4. So what you get explicitly is a problem like this, where the promise on the input has changed a little bit and the condition has changed a little bit, but it's morally the same as the problem we started with. Okay, so I hope you'll believe me when I say that all of these problems are the same. So this gives us our locality result for larger, or hardness result for larger locality circuits. We just do those 2 steps. We find a large collection of inputs with non-overlapping light cones, and we fix everything else. So the circuit is now one local, and we just argued that it solves one of these weird variants of the parity halving problem on this many bits. And so we just used the hardness result we had for the game to get hardness for this local circuit. Right? And it's slightly worse because the players can collude to some extent, or the inputs can collude. Yeah?
So they're restricted. Is it correct to say that the restricted game has omega n over L squared inputs and then n outputs?
Yes, so there is actually a mismatch between inputs and outputs. I was hoping no one would notice. The hardness carries over, but you have to keep track of inputs and outputs, and it's some work. Okay, so this more or less finishes NC0 hardness because, of course, any NC0 circuit has local hardness, or constant locality, sorry. Right, a circuit of depth D with fan and F gates will have locality at most F to the D, but both of those parameters are constant for NC0 circuits, so you get constant locality, and you get this result that an NC0 circuit will succeed with small probability, or a half plus a small amount. Okay, so the last step is AC0 for this first problem. And the problem with AC0 is that all our locality arguments won't work anymore. Because you can just have an unbounded gate that immediately touches all the qubits. So we get an opportunity to use some circuit complexity theory, specifically the switching lemma. And so the switching lemma, and this is a super high-level description of it, is that if you have an AC0 circuit and you restrict a fairly large subset of the bits randomly. Then with high probability, you'll produce a circuit with manageable locality. Okay, now obviously there's a complicated trade-off between how many bits you restrict and the locality you get and what probability this happens and the size of your original circuits and its depth, but ignoring all of this complicated interaction between parameters, you can prove some nice things by applying the switching lemma. More or less, whenever you have an AC0 circuit, you apply the switching lemma and it gives you an NC0 circuit. Okay, so let's just do that to our problem. Let's apply, imagine we had an AC0 circuit solving the problem and apply the switching lemma. So the locality gets reduced, the circuit ends up solving one of these restricted variants, and the parameters are good enough at least that the probability of success is a half plus little o of 1. Okay? Now, later on, we'll improve this. You have lots of room to play with the parameters of the switching lemma, and so we'll eventually get something more like even an AC0 circuit of exponential size ends up solving it with probability half plus exponentially small. But we'll talk about that a little more further on. Okay, so that's the first problem. It's in QNC0 as long as you have a cat state to feed it, and it's not in AC0. So we want to fix the part about needing the cat state. We want to get rid of the cat state, so we're going to define a new problem. And I'm not going to do it immediately. I'm going to sort of take some time and construct the problem organically. Okay, so the cat state can't be constructed in QNC0. So that idea is out. We have to do something else. So we'll construct something that's kind of similar to a cat state. And it turns out the best we can do in QNC0 is construct what we call a poor man's cat state. So it's something like this, where you have a bit string z and its complement and a superposition over the two. But there's a whole bunch of caveats. So you don't get to choose z. It's uniformly random. You don't even know what z is. You're given some information d that describes it, but it's not literally z itself. The best you can say is that you can recover z from this vector in AC0. Okay? So this looks kind of like a cat state. It's sort of promising. So let's see how to construct it. And the idea here is to build a tree where you have a qubit at every vertex, initially in the plus state, so the whole thing is sort of a uniform superposition, and then start measuring edges, right? So you measure the parity of each edge, right? The parity of this vertex and this vertex goes on that edge, and so forth. Okay, and this collapses the state until only a few branches of it are left. Specifically, you've got 4 linear equations here and 5 qubits, sort of 5 dimensions. So there should be 2 vectors left. Thank you. And it turns out they have to be complements of each other. And, well, this is one of them, 0, 1, 0, 0, 1. Okay? So, right. Even better is you can figure out what z has to be by fixing a starting vertex and letting the bit zi be the parity of the path from your starting vertex to that zi. Right? You can check that for all of the vertices here. Oh, I guess I got rid of the spurious labels, but they're all the path from a starting vertex to some other vertex. Okay? And the paths are unique, so this is well defined because we started with a tree. So after doing all of this, we're left with some state, some poor man's cat state on the vertices, and we also have these edge measurements hanging around. So we'll just return both. Okay? The only thing left to think about is what sort of tree to use for all of this. And well, we want two things. We want the tree to have low degree, because you have to do all of these measurements, and you can only involve a vertex in one measurement at a time without increasing the depth. And we also want the tree to have low diameter, because, as I said, we want to compute parities along paths to figure out what z is. So we take the obvious answer, which is a balanced binary tree. It has a nice low degree of 3, and the diameter is logarithmic, which is convenient because AC0 can compute logarithmic size parities. Okay, so just hold on to that fact for a second. We'll come back to it. Okay, we've computed this poor man's cat state. We have a quantum circuit that does this. It computes a cat state or something like a cat state and some extra information. What if we just plug this cat state into the algorithm we had beforehand, right? And see what happens, define our problem based on that. So that's what we'll do. And I want to just take a moment and notice that this poor man's cat state is actually a regular cat state where some of the bits have been flipped. So here's a flipped kitten for you. And then we'll do exactly what I said. We'll plug this weird state into our old circuit and see what happens. And I have this circuit identity for reasons that will become clear. So we have our old circuit for the problem, and we plug in this cat state, except some of the bits have been flipped. And we want to sort of push those bit flips through the circuit. So when we push them past the phase gates, we pick up controlled z gates. When we push them past the Hadamards, they become z's. And then when we push them, well, measurements don't care about z's, so they go away. And then we can push the controlled z's past the Hadamards as well and get controlled x's. So the takeaway is that if this bit was flipped in our poor man's cat state, and if x1 was set to 1, then we flip y. And we get the opposite of the parity that we expect. So we basically have the same problem as before, except with this correction term, which is an inner product of x and the vector z. Now, in order to know what the vector z is, we have to output d, the vector of edge measurements that we had. But basically, since we've constructed this problem from a quantum circuit, we know that a quantum circuit exists. That half of the proof is done. The other half is to prove that it's hard classically. So let me do that and then just wrap up. So imagine you had an AC0 circuit for this problem. Obviously, we're going to reduce back to our original problem, because that's what we proved hardness for. We spent like 15 minutes on it. So we're going to output this vector d. That's just in the definition of the problem. From that, we can use AC0 to compute what z must have been, because of the fact that every bit of z is a logarithmic size parity. And then once we know z, we can get rid of that extra term that we had. And sort of the details of how you do that would be to compute, the individual terms of the inner product and then XOR them off the y. And what you'll get at the end is that y is half the Hamming weight of x mod 2, which was our original condition. And so the circuit solves the parity halving problem with the same probability, and so you get all the hardness for this problem that you got for the original problem. So that's the entire main result. I guess how much time?
That was 30.
Oh, okay. Really quickly, you can get exponential here. You can repeat the game many times, and that'll make it harder if you insist that they win all copies of the game. So you can get a half plus exponential down to exponential. And you can also even get this when the circuit is exponential size. Okay? And we can reduce this problem to the hidden linear function problem. We can also make it local, embedded into a grid, and do all these nice things. And I guess I have a couple of open problems, but I'll thank you, and there.
Questions?
Is it clear that the previous problem is solvable in AC0, and what is it?
Sorry, in QNC0?
Yeah, in QAC0.
Well, we constructed it from these two parts, right? The part that generates the poor man's cat state, and then just the same algorithm that we used before. And we have algorithms for both, so you just sort of concatenate them together. That's all we're doing.
Anyone else? Yeah.
So I'm looking at the partial result, and it looks like a separation between AC0 with mod 2 gates and QNC0 Q poly.
Oh, yeah.
Is
that's
that
right.
using the same problem, or is it a different problem?
No, it's a different problem, sort of unrelated. It's instead of mod 4 and mod 2 in some sense, it's mod 3 and mod 2 or something. Yeah.
Okay, thanks.
Still got time.
Maybe I missed something basic. I just wonder, you say like it's impossible to get decision problem separation between QAC0 and AC0?
Between QNC0 and AC0, I'm not sure. Is there something obvious?
Which weighting was separated?
I mean, I think maybe I'm not sure I get it right, but like in the very beginning, you say you want to look into the relation problem
Yeah.
because decision problem is impossible.
Right. Well, for QNC0 and NC0, that's certainly true because they're the same class. But for QNC0 and AC0, I think they're different.
So QNC0 is just NC0 for decision problems. So you can't
Right.
separate from NC0.
AC0 contains NC0, so you wouldn't get the direction that you want, I think.
Sorry. So the question I meant to ask before is it clear that the previous problem can be solved in AC0? No, right?
No, we don't
No,
want it to be
it's-
solved
we
in
don't-
AC0.
No, the original Bravi-Gossett
Oh,
but
no, it definitely shouldn't
it's-
be solvable in AC0.
should.
We proved that. There was a step which I
Our problem reduces to
zipped
AC0,
through.
like the Bravi-Gossett problem. Our problem's easier than the Bravi-Gossett QNX problem. So our problem is already not in AC0, so therefore the Bravi-QNX problem is not in AC0.
What he said. or this point.
Okay, let's thank both of the speakers for their very nice talks.